I will talk to you about what comes maybe as a step 2 in your vector search journey, what comes at the point where you have figured out how to search your text with vectors, and you want to include your other data to also take advantage of it in vector search. You know, we are going beyond strings into our metadata. So for the 2/3 of the room that did not raise their hands or have not been on any event in San Francisco in the last 4 years, vector search runs on these models that turn text into vectors, okay? Vector is just a set of coordinates in some space, and this model does it in a way that clusters similar things together, okay? So we have wolf, dog, and cat together, and banana and apple on the other side. Text to a point in a coordinate space. These models are pre-trained by the foundational model companies, and we use the pre-trained models. Maybe we fine-tune them. If all you have is numbers of or names of apple trees, you probably want to fine-tune your embedding model to understand differences between those very specialized names. Okay, but those people that have raised their hand, that they have some vector search running in production, hopefully, they know that it's not just about text. Like, there is no single database deployment out there that would just be about searching text. There is all kinds of other data that enters the picture. So here is an example of, in e-commerce, you would have products, they would have rating and a description, and somehow you have to deal with that number there to make a vector again and have that map and all those benefits that you have discovered when you launch vector search system first. So what do you do with those numbers? And here comes the main villain of the story. All the vector search deployments out there that don't work with custom models trained from scratch, they work with those text embedding models. And the text embedding models can't deal with numbers properly. So just a quick experiment, you can replicate at home, do try it. Take 100 numbers from 1 to 100, stringify them, encode them with OpenAI embedding model to get these vectors out, and then make this chart. This chart is done by grabbing the vector that encodes the number 50 and calculating its similarity to all the other vectors. And what you would expect if the model actually understood numbers, you would expect that similarity to drop along that orange line, right? So 50 is the same as 50, and then it drops as we go further. However, this is not what happens. You get the black line, you get noisified, right? The text embedding model tokenizes your stringified numbers as text tokens, and then it runs those tokens through some big neural network trained on how these numbers co-occur on the internet, and it has basically very little concept behind how, what those numbers actually represent. And so if you just stringify your JSON, run it through a text encoder to make vectors, you will get about this quality of vectors out of it, which it's bad. And then, in practice, it only gets worse, because if you have seen some kind of Elasticsearch deployment out there that has been running for a couple of years, you know that those objects have tens and tens of different properties, sometimes hundreds. And those properties have, are numbers and locations and lists of IDs to other objects. Obviously, this is not going to work. You can do vector search for their descriptions, but how do we get to the object level vectors? And basically, the reason we would care about that is who out of you can tell me what this user is searching for? So this is a search query on an e-commerce website. What does this person want? Okay, wisdom of crowds, guys, come on. Yeah. So e-commerce website, I come to the website, I type this query, what am I buying? Toothbrush! Yes, excellent. Certain kind of toothbrush, right? But I have a problem and I describe it. If you have a search box on your website, you should look at the search logs, because people have learned from ChatGPT not to describe the thing they want to buy, they are describing the problem. This is like a shift in user behavior caused by by these sort of chat-based interfaces. And good luck dealing with this kind of query if you don't encode everything you know about your products into vectors and then do the same thing for your queries. It's not going to work, right? And in practice, then it's also about other kinds of things you want to take into account, right? It's not just the relevance of the query, but you want to skew towards popular results. You want to prioritize highly rated items. The user has context of location. This is complicated. And your search system ends up looking like mountain range. This is Elasticsearch query as a JSON object, rotated 90 degrees, that tries to describe. This is like a very simple example. These queries usually have hundreds and hundreds of lines, and you do boosting and hybrid search, and pre-filtering and post-filtering, and it's just crazy. The mental model is wrong, right? How can you iterate and improve this kind of system? You can't. And so basically, in my talk today, what I wanted to just establish is that we need a new mental model for thinking about complicated information retrieval systems. And the model that's actually kind of consensus already in certain circles is that you should just think in vectors. Okay? What does that mean? You need to turn all your users into vector embeddings, all your products into vector embeddings, all the queries coming in need to be encoded in this way, and they all need to be in one shared coordinate space, so that when you get a query, cheap cleaning with braces on, coming from a user, you can take average of those two. Now you are doing personalized search. And then with that point, you can look at what's around it in your catalog and actually get to a result that takes all those concerns into account in one unified mental model. And the last problem here is, how do you make those points? How do you create vectors that encode all those different aspects of the product that we talked about? Normally, you train encoders for this from scratch. This is what I was doing at YouTube for 6 years. You need about 3 to 6 months per encoder, bunch of smart people, lots of data. So this is basically not really viable for most companies. And now is the part where I tell you what we actually do. We have an open source, free to use Apache 2.0 framework that helps you assemble object level encoders for your data, and then use those vectors these encoders produce for search, recommendations, retrieval for agents, that sort of thing. Okay, who, with a show of hands, understood at least 75% of what I said? Yes. Very good. You guys are very kind, or you actually understood. Either way, that made me happy. Okay, how do we actually do this? How do we transcend the inherent limitation of a text embedding model that can only eat text? Have you guys heard about the mixture of experts? Mixture of experts in large language models, where the model is basically, it contains a number of kind of submodels, and each is optimized to solve a different task. And then there is another layer that figures out, okay, which expert, which submodel should be used for a given query, and then the outputs of the experts are merged, and the result is produced. This has been done since the beginning of the LLM movement, right, to improve performance and make the model smaller. We apply similar solution to embeddings with an important difference. For us, the experts are all different encoders that can eat different kinds of data. Okay, we have encoders for numbers and graphs and location and all these kinds of information that you need a dedicated, specialized encoder for. And then we have a framework that you can basically use to combine these components to make your own embedding model, or embedding models, many models. And through that, create user vectors and product vectors. So if you are running a marketplace, for example, this is the kind of thing that helps you. We work with companies from travel to fashion to jobs to used cars. We help them all sell more T-shirts and and book more cars and book more hotels by helping them crystallize everything they know about, let's say, a hotel into one single vector, right? This is the key observation. And then our product runs on top of a vector database. And I'm 100% sure you all heard about vector databases. This is not possible to not hear about. So we just sit on top. We make better vectors. The database is indexing them together. This is a solution for search on top of complex data. There is a bunch of use cases. You can scan the QR code to get into our documentation. As I said, the product is free, so I have nothing to sell you, basically. There is a cloud product that's coming out that helps you scale this thing, and then that will be what we'll be selling. We have a comparison of 47 different databases. That's our main kind of community project. This is open source. It compares these databases across 47 different features. We have a bunch of content about building vector-powered products. And now this is the main step of the presentation. This is the main QR code. And it goes to our GitHub repository. And you have been in Silicon Valley for a while, and you have realized that this whole place runs on GitHub stars. And so we have an open source framework that's free. And the only way you can help us out is not YouTube subscriptions, is GitHub stars. So if this topic is interesting for you, you want to follow along, that's the best way to do it. How is the time? I think this is kind of it. Any questions? Yes.
Yeah, I thought the inventions are different. Like the LLM, it's going to combine LLM. How would that work?
So this goes beyond LLMs. So language, imagine on the very simple example at the start, okay? You have an object that has one bit of text and a number. You somehow need two different models, one language model to eat the text, one number model to eat the number, and then you combine their output to make a vector that encodes both of those things together. And so now when you have a query that's like, popular toothbrushes, the word popular refers somehow to the numeric aspect of the data. The word toothbrushes refers to the textual aspect of the data. And this query can now be resolved with vector search. It integrates together. This is why, one of the ways we call it is metadata-aware vector search. It integrates together all these different concerns so that your user can find the thing they're looking for. But
that should be more mathematic.
No, it's next to it. So imagine there is language model that eats the text, produces a vector. Next to it is another expert that's like a number encoder, eats the number, produces a vector. This next one eats location, produces a vector. Next one eats an image, produces a vector. And then there is another layer under that stitches those vectors together, different ways to do that. And the point is that at the end of that process, you have one big vector that encodes all these things in accurately, not like stringified number, tokenized as string and encoded with a text embedding, but something that is meant to encode numbers or locations or whichever other data type you have.
So that you have an LLM that takes a query from customer, then it gets mapped to your.
That's right.
Yeah.
Yeah. So how do we go from the natural language query that describes all kinds of different aspects of the data and take that and make a search vector out of it to go search in the database? We do it by first breaking the query into components, feeding those components into these individual experts, producing, let's say the query mentions popular, so the number encoder knows to create a bias towards highly rated items in its output. If it mentions hotel near Manhattan Midtown, then the expert that deals with location will know to create vector that skews towards this location. Each expert is dealing with each of those kind of aspects of the query, and then those are all merged together, and you get a search vector out of it.
I guess it's just okay. So what is the element? So it gets it down as a sort of that's included, but I mean that.
Well, you can make LLM do many things. Yeah, that's kind of part of the solution and part of the problem. Yeah, but yeah, there is like query understanding step, and then there is the embedding of the components step, and then the kind of combination at the end. By the way, the paper that described mixture of experts as approach came out, I think, 2 months before the Transformers paper in 2017. So that's like a good place to start checking it out. By the way, I'll keep doing this until you kick me out of the stage. So we're doing this. Yeah.
But it's just different. And I don't really is that but with data within the city with raised on hold, not the list of cloud you got the
And then doing like embedding with the text. Yeah. Basically this. Like this contains the answer to your question, understanding why the black line is like that. That's the hurdle you have to get yourself across, because this is how, no matter what fine-tuning you do to a text encoder, it still operates in the same way, which is it tokenizes the input. It basically looks up the embedding of each token and runs those embeddings through a neural network. And the fine-tuning is like tweaking that, basically, but it doesn't change the fundamental way the model sees the world, and that's through those tokens. And if you have numbers on the input, they'll be treated as text. And this is where it basically the noise is injected, because they are treated as something that looks like a number, and the relationships between these numbers are inferred from training data that contains some references to numbers, but nowhere in the model does it say 49 comes before 50. This is not encoded in there anywhere. And so it's always going to be like a probabilistic thing, but it's a number. It shouldn't be probabilistic. Like if I ask for popular things, give me the things with high popularity, right? This is not a probabilistic problem, right?
they're really basically
I mean, that's just the way you encode your input to this process. You can have Parquet file, JSON-L, whatever. It's just how do you go from that file to the vector? That's where the modeling happens, and that's where you want to be kind of in tune with the data on the input. If it's text, use text model. If it's latitude, longitude, don't use a text encoder to encode an address, because it's not, the model doesn't have a map in it, basically.
That's not a bit. It's rather than business. And when you really praise that.
Yeah, I mean, so by the way, this goes for everybody. If you have a question, you can connect with me on LinkedIn. This is my preferred place to connect. My name is, you can just look up the company. There are not that many of us there. Superlinked. Connect with me, and I'll help you figure out all your vector problems. Last question. Somebody who, let's do this one, yeah.
Maybe we talk about the data between those that that there's some quite true vector data that comes set up.
Yes. Very, very good question. We are not a vector database, guys. So we sit on top, we make vectors, and then we work with vector databases to index them, right? So Superlinked box in the middle, vector database boxes under. We work with Redis, Mongo, and Quadrant. There is more coming. The encoders or the experts we have are, by the way, graph, so relationships, right? Graph embeddings are obviously a big deal, but also like other data types. And then those are stitched together to make these, where you stitch them together to make your own models that feed your data. And then the input is whatever, for example, JSON, and the use cases are, information retrieval use cases on top of combinations of structured and unstructured data, RAG, search, recommendations, analytics, and so on. All right, I think that's it. I'll be around for the happy hour. Come find me, and connect on LinkedIn. Give us a GitHub star, and I hope you enjoy the rest of the event. And see you around.